Alright, welcome to Concept E. We're going to be focusing on what we consider the Bronsted Lowry theory of acids and bases. We've previously talked about the Arrhenius theory, and the Bronsted Lowry came after it and kind of builds upon it and expands it to include more acids and bases based on the definition. So previously we've talked about the production of hydrogen or hydroxide ions and using that to identify acids and bases. Today we're going to change that a little bit for this alternative theory. Now the Bronsted Lowry acid is a species that can donate a proton to another species. And remember, a proton in this case we're referring to the positive hydrogen ion that's lost its one electron, so it has a single proton remaining. So acids donate, and then our Bronsted Lowry base is going to be identified in the fact that it can accept a proton from the acid or from another species. Now, for example, here we have hydrofluoric acid and water combining. Now, HF is going to donate the proton and thus is the acid. The big thing with Bronsted Lowry is you have to be able to compare the reactant side and the product side to be able to see who's donating, who's accepting. So HF again is going to donate that to the H2O so that F is by itself. The fluoride ion is by itself, and then hydronium is produced. And just remember, the production of hydronium is responsible for the acidic properties. So the hydronium ion in solution would make overall the solution acidic. Now, the Bronsted Lowry definitions explain why substances such as ammonia, which has no hydroxide ions, will act like a base in water. Because again, ammonia wasn't able to really be defined as a base under the Arrhenius theory, but Bronsted Lowry does allow it to act like a base, and let's show and go through that. In this case, again, H2O, if you compare left to right, H2O has lost a hydrogen ion as it goes from being H2O to OH, and NH3 is going to accept the proton from water, and because of that we have a hydroxide ion formed, thus producing a basic solution. So again, just keep in mind, in this case especially with ammonia, because it's accepting that proton and forming hydroxide ion, because of that we're able to produce a basic solution. Okay, so remember the species that accepts the proton is our base. Now, ammonia is amphiprotic, meaning that it can act as either an acid or base depending on the situation. And if you've been paying attention, we've talked about how water can act as an acid or a base depending on if it's donating or accepting that proton. So you might want to go back through and look at those two examples that we did earlier. Alright, so very last part, we're just going to look at looking at the forward versus the reverse reaction. So in this case, we consider the acid HX in water. And we look again from left to right, we're looking at the donation and acceptance of a proton. Because HX is going to donate that proton, it's considered the acid. And because water accepts the proton, it's going to be our base. And again, this is causing me to look from left to right. So HX is going to X, so I've seen that it's lost it. And H2O is going to H3O, meaning that it's gained it or has accepted it to be our base. We also have to be able to look at the reverse reaction. And this is going to be incredibly important in tomorrow's concept because we're going to be able to need to do this in order to pair up conjugate acids and bases. Now, H3O plus and X, if we look going from right to left, H3O plus is donating the hydrogen ion, our proton to be the acid, and X is accepting it to become our base. Alright, and we're going to spend a lot more time going over this in class tomorrow, but it's definitely something that you want to get a head start on.